Good morning, everyone. Can you see my presentation?
Yes, we can.
Okay, good. Good morning, everyone. It's my pleasure to give a short description about ultra-fast transition transformation in material systems and the activities that we are performing within IMPRESS project. Uh, to summarize my talk, I will give you a brief introduction about the time result measurement in TEM, and then immediately we go through conventional approaches that has been applied or employed in the TEM community. Then I will switch to the major modifications that we have made in our instruments to perform such experiments. And at the end, if time allows, I will show you some examples about our works over last 2 years. Uh, okay, when we talk about the time result measurement in TEM, indeed, we are going to study a specimen before and after the transition. What do you mean by this? Uh, there are different a sample in a TM, will say in a steady state in ultra high vacuum condition, and then we apply a stimuli to the specimen uh, and cause a change into the specimen condition. Depends on the condition and the reaction time. There are different time domains in which we need to observe the changes. As you can see here in this overall my um, graph, it can be from hours up to femtoseconds. Basically, in microscope, we work in the second regimes here, but with the time resolve measurement, we would like to go through the shorter or smaller time domains, which ended up in femtosecond with light or magnetic field stimuli on the sample, which goes through magnons, phonons, and spin configuration in the specimen. One thing which is important to explain here is that there are different ways. So, if you would like to study short phenomena with a short lifetime, you should have either a super fast camera or detector. Of course, you can apply a short pulse, any kind of pulse to the sample, and you should have a short source. This source could be electron source or X-ray source or laser source, either of them. So for any imaging system, you need to have a short source, uh, fast stimuli on the sample, and fast detector. As you have seen also in Azure Talks in 5.3, the fastest detectors now works in the range of nanosecond. So this means for shorter time domains, we cannot work with the fast detectors. We need to provide enough electron or enough signal and pass a stimuli on the sample to be synchronized with the detector to be able to observe ultra short phenomena or transitions in material. Uh, there are commonly two approaches in TEM community. One is laser based and the second one is laser free based to provide short electron pulses. In the laser base, you will pump your electron with a laser beam to create a short electron pulse. You can tune your laser beam, of course, with different electron guns to go through a single frame or go through a stroboscopic mode. In a single frame, you need to send a huge and very strong laser pulse to your electron beam, create a huge amount of electrons, typically 10 to power 8 or even 10 to power 10 electrons per pulse, and to have enough signal to form an image from your sample. And then you will synchronize. Maybe I can go to, no, sorry. Uh, laser. Okay. Then you will synchronize your source pulse with your pump pulse. And then when you pump the sample with uh, an stimuli, like let's say uh, electrical signal or laser pulse, then you will send a laser pulse to your electron gun, and then you will capture an image. It can be extended to a kind of so-called movie mode when you send a train of pulses to your electron source, and after creating a change in your material system, then you will study the evolution in the sample with a very short time intervals. For example, if you are studying a crack growth, uh, or for example, if you are studying a melting condition or nucleation, these are you can have snapshots and 9 or 16 images or frames from the evolution of the specimen after the pulse. More common way is the U-10 when you send a much weaker laser pulse to the UV pulse to the electron gun, and then short pulse which is synchronized, so there should be a delay line because of the difference, geometrical difference between these two sources, and then study the sample, which provide, of course, much less signal, but it would be a stroboscopic measurement, so it works for reversible phenomena, for example, a spin transition or plasma transition, something like this, and then or PNM, and then you will collect enough signal to create a to be able to create an image or a spectrum. The different approach is that you will not modify your electron gun, but with a laser pulse, which is quite troublesome, but you will install a beam blanker based on different technologies, and then you will sweep your beam over an aperture, and then in this way you will create electron pulses, which reaches to the sample. This Either of these methods has its own advantages and disadvantages. Either of them has its own time domain. The fastest, of course, would be U-TEM approach with a short pulse in femtosecond. D-TEM pulse would be working in nanosecond or microsecond, and the best performance of the electrostatic beam blankers at the moment in the community is about a few picoseconds. So you have a full range of time domains to study different phenomena. Um, okay. In Jülich, what we have done, we have worked with Euclid Tech Labs, and we installed a ultra-fast pulsar from their technologies based on two kickers, which are working based on microwave cavities, and which create the first one we sweep the beam, then we have aperture to create a pulses, and the second kicker will provide uh, a stationary electron pulses. This is the hardware of the cavity. I will not go through quite a lot in detail about the structure of this cavity, but we can discuss it in the break room. There are some optical elements to control the quality, shape, and coherence of the electron beam. And with this, we can create in two different modes, different pulses. In RF mode, in pulse picker mode, which is based on electrostatic sources, we can provide 150 to 300, for example, picosecond pulses with different repetition rates. And in the continuous mode, when there are RF, the kickers or the blankers work based on the radio frequency sources or RF sources, it would be sinusoidal electron wave. And then we will have up to 12 gigahertz, which goes, for example, for less than 50 picosecond. And then we can study the specimen in this range. The fields that we can go through this study are quite wide and diverse. We can study magnetic transformation in different material. We can study the electric field mapping in different semiconductor devices, junction potentials, and so on. We can study phase transitions in different material systems, and especially in 2D materials. We can go more and study the dynamics of the magnetic vortex core uh, in a time-resolved manner. In a phase transition material, for example, phase change or uh, material system, we can study perform diffraction study to see their evolution after each pulse. And of course, for neuroformic material system, we can study the switching of the ferroelectric domains in different material systems. To use this system, normally we work with a special holder, which is based on also excitation of the specimen with radio frequency signals. As you can see in this graph, there is a RF generator. One will go through the electron gun and not exactly the gun. Gun will be in CW or continuous mode condition, which reach to the ultra-fast pulsar or ultra-fast blanker, which create electron pulses, and this will be synchronized in some ways with the stimuli which receive to the sample and excite the sample in different conditions. So in this case, you can assume that you don't need a fast detector. You just need a good detector or normal detector even, and the signal will be synchronized between your electron source and the stimuli or the pump on the sample. And then you should be able to perform a pump probe experiment. Uh, Now I would like to give you some examples about different activities that we have done so far in within Impress project. To just give you some hints what kind of studies we can do. The first system is ion scene sample. In this sample, we can create magnetic bubbles with mixture of magnetic bubbles and helical phases in room temperature. And uh, okay, if we go down, just if I can play this video.
Maybe you have to remove the pointer for a
Yeah. Okay. So now you see this video. And you see these circles, which are magnetic bobbers, and there is sometimes a white or black dots, or sometimes there is no dots in the center. These are a small skemion at the center of these bobbers. Uh, each frame in this movie is one is recorded after one single laser pulse. You can find all the specification here. This experiment has been done in room temperature, zero applied magnetic field, and these are the properties of the laser beam. And in this way, we can somehow, in a controllable way, we can control the magnetic states of these bubbles and switch the core or polarity. This is another movie from the similar material system in which we are studying the similar condition with much longer laser pulses, 2 picosecond in this case. And then you can see the changes also not only in these magnetic bubbles, but also in the helical phase and the stripes that are formed. As you can see, at different points, at different slides, they are changing. And this gives us a hint how to create and design novel material system for next generation of spintronic devices. Um, okay. Um, there is a second experiment example that I would like to show you. This is about the cobalt zinc mangan, which also represent skyrmions at above room temperature. There have been some studies on this material system to characterize the magnetic characterization, but here we are focusing on, again, similar experiment. This is a single shot experiment like DTEM experiment that I explained before. When we send a single pulses and we can manipulate single skyrmions, cluster of skyrmions, or very small lattices. So as you can see here, the skyrmions are changing or increasing by the time. And this is the first time that it's shown in the community that the skyrmions in magnetic system can be created at room temperature at zero field. Changing a little bit the condition of this, no, it's repeating. Okay. Here, with a little bit more stronger laser pulse, what will happen? You can see much higher activity in the skyrmions, and in some individual snapshots like this, you can see we can create skyrmion bags like this or different exotic magnetic texture, which are not common in conventional studies. So this is another possibility for this kind of studies when you can create novel magnetic textures by a laser pulse. And the reason is that with any laser pulse, you have a very sharp thermal gradient that can create uh, bring the sample to above the Curie temperature and then leave it in a metastable state, which you can see novel textures which are not possible by normal heating or cooling or biasing experiments. Eventually, I would like to show you one more example about the junction potential. This is a Schottky potential, a device for Schottky potential based on silicon oxide, and some metallic layer on top. And then we studied the potential junction during light on and off. So here is light off and here is light on. You can see almost 2 pi phase shift, which shows the interaction of the photons, sorry, with electron holes. So changing the carrier inside the junction or the material, which would be quite important for example, solar cells and photovoltaic system and so on. Uh, that's with this. I will end up my presentation. That we have installed a ultra fast pulsar in the gigahertz regime in our microscope and would be able to run home probe experiment without major modification into the microscope with introducing laser beam to the gun. And we are working collaboratively with Eli, Eric, and of course the Sprint Lab in and CNR in Trieste on new material system and correlative techniques to study these fast transitions in different material systems. We have defined different workflows for ultra-faster transitions, and I showed you some examples, and there will be more examples maybe in the next workshop, or if you follow the Impress newsletter, you can find them in the public reports. And yeah, we hope to take advantage of the interoperable platform that Regina explained at the beginning of the session to be able to do some experiment on identical specimen in different machines. With this, I would like to thank you everyone for listening to this talk, and I would be happy to answer if there is any question.